This is Kumaravel, Assistant Professor EC from RMT Engineering College. Today's topic we are going to discuss with L-type matching network. Let us consider a problem. Using Smith chart, we need to design two-element matching network. The given data are ZS is source impedance is 50 plus J25 and load impedance is given. Similarly, frequency is given and characteristic impedance Z0 is given. If Z0, if it is not given in the question, then we need to assume it to be 50 ohm. Okay. So now let us proceed. So first step, we need to find normalized source and load impedance. Let us use a symbol normalized as small ZS. Okay, small ZS equal to the given source impedance divided by characteristic impedance, that is 50 plus J25 ohm divided by 50. We will get 1 plus J 0.5. Similarly, we will find normalized load impedance ZL divided by Z0. So 25 minus J50 divided by 50 will get 0.5 minus J1. Next step, step 2. Step 2, we need to find normalized source and load admittance. So we have impedance, inverse of impedance will get an admittance. Therefore, small ys equal to 1 divided by Zs. Therefore, 1 divided by 1 plus J 0.5. Okay. So now we can take complex conjugate of it and multiply it with numerator and denominator. Therefore, 1 by 1 plus J 0.5 multiplied with 1 minus J 0.5 divided by 1 minus J 0.5. Therefore, source admittance will get 0.8 minus J 0.4. Similarly, we can find load admittance. Load admittance, similar manner. So, inverse of load impedance we have to take, then taking complex conjugate of it, then multiplied it with numerator and denominator, we will get load admittance as 0.4 plus J 0.8. So yeah, in step 1, so we have calculated source as well as load impedance. In step 2, we have calculated source and load admittance. So now let us proceed. So now we will use ZY Smith chart, right, to find the matching network. So here, let's proceed. Step 3. Step 3 is plotting of constant resistance and conductance that pass through the point of normalized source impedance. So let us consider what is normalized source impedance. So we already calculated normalized source impedance. Normalized source impedance is 1 plus J 0.5. 1 plus J 0.5. So let us go to ZY Smith chart. In ZY Smith chart, so here we have, right, so this side we have constant resistance circle. On the other side, we have constant conductance circles. Okay, so now we need to draw resistance and conductance circle that pass through the point of, okay, so let us go back. We need to plot the constant resistance and conductance that pass through the point of normalized source impedance. Okay, normalized source impedance is 1 plus J 0.5. So now here we have, so let me zoom in. So here we'll have 1, okay, and 0.5, so it will be here. Therefore 1 plus 0.5 will be here. So take 1 in 1, we take color 1 in 1, I need to find 0.5. So this is the point. 1 plus j 0.5, so which is nothing but small z s, normalized source impedance, small z s. So now we need to draw a resistance circle and conductance circle that pass through this normalized source impedance. So what we have to do is, okay, yeah, so here we need to trace this path. We need to draw the resistance circle that pass through this point 1. Actually trace this path exactly. Okay. Similarly, I need to draw the conductance circle. Okay. Similarly, this side. So now I plotted resistance circle as well as conductance circle that pass through the point ZS. Okay. So now let us proceed. So next step we need to plot the again constant resistance conductance circle that pass through the point of normalized complex conjugate of load impedance. So load impedance ZL is 0.5 minus J1. So we need to take complex conjugate of it. So complex conjugate, that is ZL conjugate, which is equal to 0.5 plus J1. Okay. So now let us, so here let me take, okay, okay. So here 0.5 plus J1, therefore 0.5 here. If I trace this path, I will get 1 here. So this is the point where complex conjugate of load impedance ZL conjugate, ZL conjugate. Okay. Now again, through this ZL conjugate, we need to draw the both the, okay, to draw the resistance as well as conductance circle. Let me use a different color for this. So I need to draw the resistance circles. So draw it properly. Here I am using mouse to draw it properly. If you trace it, okay, resistance circle. Similarly, we need to draw the conductance circle. So conductance circle will be like this. Yeah. Okay. So now we have drawn resistance and conductance circle that pass through the point source impedance ZS. Similarly, resistance and conductance circles that pass through the point conjugate of load impedance ZL. Okay. Now next step, step 5. Find the intersection point with normalized impedance and admittance. So now we need to find the intersection point. So here let us find the intersection points. So what happens, these here it intersect. Similarly here both are intersecting. Similarly here both are intersecting. Similarly here both are intersecting. Let us mark the point as A, B, C and D. So we have 4 intersection. Okay, let us go back. So now find the intersection point with normalized impedance and admittance. Okay, so now for point A we need to find the impedance. So from the chart we can find, okay, let me go back. Yeah, from the chart I can find the impedance value. So impedance value I can find it as, so it will be, okay, it will be 0.5 plus j 0.6. okay, let me go back, wait. Yeah, it will be 0.5 because, so point A it will be 0.5 here, 0.5 here, from here, so it whose value is, so here whose value here is 0.6. okay, therefore whose value is ZA. Impedance at point A is 0.5 plus j 0.6. So for this impedance we need to find the, next step is we need to find the admittance. So YA equal to 1 by ZA, that is 1 by 0.5 plus j 0.6. okay, so it is multiplied with complex conjugate in numerator and denominator. So we will get admittance as, admittance at point A as 0.8 minus j1. Now let us proceed. Okay, so this is how actually, right, this is how your chart will looks like. So now for the intersection point we need to find the possible configuration of L-type matching network. So our intention is we need to find the matching network. So first let us consider, so we have source impedance, let it be ZS, and load impedance, let it be ZL. Between the source and node we need to find the components. How we can find the components? So let us consider, yeah, so what does it means is, if we trace, right, so here it will be, okay, so now we can say to be, it is an inductor shunt, okay, shunt inductor, here it will be series inductor. So in parallel here we will have series, yes, series capacitor, here shunt capacitor. Okay, here we will have series capacitor and shunt capacitor. Okay, so now let us see. So we have point A. So we need to trace the path from ZS source impedance to point A to complex conjugate of load impedance, from ZS to A to ZL. In this path we have to travel. So now let us consider it from ZS to ZA. From ZS to ZA, it is what? Constant conductance circle. So constant conductance circles we have either shunt inductor, okay, either we'll have shunt inductor or shunt capacitor. If we move in upward direction, then it will be shunt inductor. Therefore, the first component will be shunt inductor. Okay. So now from ZA, now from A, so we have to travel to ZL conjugate. So it will be in what? Resistance circle in upward direction. Resistance circle, so this is a resistance circle. So resistance circle rotation. So here in this resistance circle, if it moves in upward direction, it will be series inductor. Series inductor. Okay. So our matching network is two inductor, one is shunt, it will be L1, next one will be series inductor. Okay, similarly through point B, point D as well as point C, we can design a matching network in a similar manner using this diagram. Now let us proceed. Now we need to find, last step is we need to find the actual component value for the matching network. So in the matching network, so we have first component is shunt inductor. So now we need to find the shunt inductor. Okay. To find the shunt inductor L1, so L1 equal to minus Z0 characteristic impedance divided by j omega XL1. First we need to find what is XL1. XL1 is calculated using the sum of difference between, okay, sum of difference between, so YA, right, YA minus YS, because first shunt inductor between point what, so from your source impedance to point A, so the difference between these 2 points, that is YA minus YS. So YA that is admittance of point A as well as source admittance we have already calculated. So source admittance is 0.8 minus J 0.4, okay, 0.8 minus J 0.4 source impedance, whereas point A, for point A admittance is 0.8 minus J1, 0.8 minus J1. The difference between these 2 points will get J 0.6. Now substitute it in the previous equation, we will get L1. So we know that characteristic impedance is 50, J omega is 2 pi f, 2 into pi 3.14, f is given as 2 gigahertz, so we have considered 2 gigahertz, and XL1 is, so J 0.6, substitute it here, then we will get the inductor L1 as 6.63 nano henry. Similarly we can find series inductor also. So for series inductor, let us consider L2 equal to J XL2 Z0 divided by omega. Okay. So now similar manner we need to find XL2. The second component series inductor between point A to load impedance. Therefore, so we will have it is in series combination. Therefore, XL2 equal to ZL conjugate minus ZE. Now we will find, we know that ZL is 0.5 minus J1, ZL conjugate is 0.5 plus J1, therefore 0.5 plus J1, and ZA is 0.5 plus J 0.6, 0.5 plus J 0.6, we will get J 0.4. Therefore substituted in the previous equation, we will get the inductor value as 1.59 nano henry. So now the first inductor value is 6.63 nano henry. So let us write here, it will be 6.63 nano henry. Similarly L2 is 1.59 nano henry. So L2 is 1.59 nano henry. Yeah. So now we have obtained the required matching network. Similarly, we can find other combinations also, because we have various point, that is nothing but B, C and D. Through B, C and D also we can find the matching network in a similar manner.